Is tert butoxide anion a strong enough base to react significantly with water? In other words, can a solution of potassium tert butoxide be prepared in water? So that's the big question here. The pKa of tert butyl alcohol is approximately 18. Can you, if you take potassium tert butoxide, which is a white solid, you can buy it from a chemical company. If you put that in water, will it stay as potassium tert butoxide? Or will it react with water significantly? And if it reacts significantly with water, that means it changes. It's no longer potassium tert butoxide. That's what we mean by, can you make a solution, can you prepare a solution of potassium tert butoxide in water and it still be potassium tert butoxide after you've added it to water? So let's just see what would happen. So the question is it a strong enough base? So that's keying us in to the reaction that we're talking about here. So I'm going to make this, and I'm just going to draw this with a skeletal in a skeletal form. So potassium is our spectator ion, counter ion. That's the base, right? So this is the base plus water, the acid. If this is the base, this has to be the acid. If there's a base in a reaction, there has to be an acid. So, and we'll draw this equilibrium arrow. Usually acid-base reactions are considered equilibria, although if you have a very, very strong acid reacting with a very, very, let's say a very, very strong base, that is not really an equilibrium. You could say that that reaction just goes all the way. But let's just say, for the most part, we're talking about equilibrium. That means a reversible reaction. Now, the acid is going to donate a proton. So let's just say this proton is going to be donated to this base. The base is pulling the proton off, and I'm going to use curved arrows here to show that reaction. So lone pair from the tert butoxide, the oxygen, and that lone pair is pulling off this proton, and for it to happen, for that proton to be removed, the bond between the proton and the oxygen in water has to turn into something. In this case, it's going to become a lone pair, and the conjugate base of water will result. And let's just draw the conjugate acid of the base. So now this is the conjugate acid of our tert butoxide, which is tert butanol. And then what happened to our acid? Well, it became the conjugate base, OH minus conjugate base. Now, the question is, actually, this is the question. Will it react significantly with water? So is this equilibrium best represented like this, with a big forward arrow and a little reverse arrow? That would indicate a significant reaction. So this one right here, mainly forward and barely at all in the reverse, this is a significant reaction. If we have the opposite situation where you have just a little forward arrow and a big reverse arrow, this is little, well, I'll just say very, very little reaction. We can also say that in this case, the equilibrium lies to the left. And in this case, the equilibrium lies to the right in the equation. So if the equilibrium lies to the right, that means that there is a significant reaction, and when you put potassium tert-butoxide into water, this is what happens. You have tert-butanol and OH-, which means that you can't prepare a solution of potassium tert-butoxide in water. Otherwise, if the equilibrium lies to the left, that means that there's very little reaction. You can put potassium tert-butoxide in water, and maybe a little of it will turn into tert-butanol and OH-, but at equilibrium, you still have potassium tert-butoxide in water. That's the question. Now, how do we figure this out? Well, we're given a big hint here, which is that the pKa of tert-butyl alcohol is 18. So if the pKa of tert-butyl alcohol is, actually I'll put it over here because this is the tert-butyl alcohol. This is the acid that we're talking about. When you talk about pKa, you're always talking about the acid. This is the acidity constant. So this is tert-butyl alcohol. I'll put this in a different color here. And alcohol simply means it has an OH, and we'll learn all of this nomenclature later. The pKa is about 18. Well, that doesn't tell you much. You have to actually, what we're looking at when we look at whether a reaction happens or not is the relative pKa's of the two acids. So the other acid in this system is water, and the pKa of water is about 16. I think it's 15.7. You can tell I haven't memorized my pKa's to the first decimal place, but let's just call it 15.7. It's closer than 16. All right, so the question is, how does this equilibrium lie? Is it here or here, given these two pKa's? Well, the equilibrium, this is the big reveal here. The equilibrium lies toward the weaker acid. The equilibrium lies toward the weaker acid. And by definition, the weaker conjugate base. Because, remember, the weaker acid, in this case, this is the weaker acid because it has a higher pKa than this one. So if this is the weaker acid, its conjugate base has to be stronger than this one. So this is the weaker acid, and this is the stronger acid because of the difference in pKa, 18 versus 15.7. Therefore, this must be the stronger base and the weaker base. So, because the stronger base turns into the weaker acid, tert-butoxide and tert-butanol, and the stronger acid turns into the weaker base, water versus hydroxide. So the question is, can you prepare this? Well, the equilibrium lies toward the weaker acid and weaker conjugate base. So the equilibrium does lie toward this direction, the direction that we put the arrows in the first place, which means, and how much, to what extent? Well, the pKa, the delta pKa is, let's just call this 16. The delta pKa is about 2. And remember, pKa is a negative log. So this is on a log scale, which means that the equilibrium, the KEQ, is 100-fold to the right. Let's say, lies 100-fold to the right, or this right arrow should be 100-fold bigger than this left arrow. Or at equilibrium, you have 1% potassium tertbutoxide and 99% tert-butanol, which means that no, you cannot prepare T-butoxide or tert-butoxide in water to any significant extent. You'll just be making a solution of tert-butanol and hydroxide.